It gives me really terrific pleasure to introduce Ron Breiger. He's one of the giants in network analysis, especially in the social sciences. I've known of him for about 15 years, perhaps longer. Maybe actually dating even longer, I'm not sure. But actually, this is the first time that I've met him, even though we emailed occasionally. So it's really a terrific privilege to welcome him to the Yale Institute for Network Science. He's professor of sociology at the University of Arizona. It kind of looks like East Rock, but it's much better, I think, what they have there compared to what we have here. He's won a number of accolades over the course of his career, including the Similar Award from the International Network for Social Network Analysis. He was the editor, which is thankless work for social networks for quite a number of years. I saw it had an end date as well for your duties, yes, which was very welcome, I'm sure. And he has diverse interests in network science. One of the things I like about Breiger's work is that he both innovates methodologically but finds beautiful applications to some of these novel ideas. And I think one of the nicest things you can say about a scientist is that he or she invents his own tools, right? So famously, Galileo invents the telescope and sees new things, or von Leeuwenhoek invents the microscope and sees new things. And Breiger invents new methods which allow him to see new things, which is very impressive to me. His interests are broad, include social networks and adversarial networks, something we are very interested in my lab right now. We call them antagonistic ties, he calls them adversarial ties. And most recently had a monograph on big data and society, another topic about which he's thinking. So join me in welcoming Ron Breiger.
Thank you so much, Nicholas, for that very, very kind and generous introduction, and thank you as well for inviting this visit and arranging for it. I see many friendly faces in the audience. I thank you all for coming. So I'm going to talk about something that is methodological. I'm going to talk about a method for community detection, but I'd like to talk about them in a way that makes some connection with wider issues and leads to, in a certain sense, to some reconsideration. Okay, so let me start with the community structure problem, and this is owing to Mark Newman, a brilliant and prolific contributor to network science. The community detection is absolutely a bedrock of much of what is done in network science. In brief, the problem is finding natural divisions of a network into groups of nodes such that there are lots of edges within groups and few between them. So here's a stylized example. The basic idea is suppose we didn't have these dark circles, suppose we just looked at the ties. Might there be some way that we could discover communities where communities are defined as having relatively high number of ties within communities, relatively low number between them? Why might this be an interesting thing to do? Well, there are many reasons. To take just one example, think about mapping the entire field of science. Suppose the data are networks of co-citations. Well, we'd be interested in specialties, we'd be interested in subspecialties, we'd be interested in things on the edge that appear maybe at the interstices of existing areas that might turn into new ones. Mark Newman, as well as other people, such as in sociology, James Moody, have used community detection to locate specialties and research groups and communities of practice within science. This is one of many, many, many applications of community detection, and so it's useful procedure and project to think more about. It's used often as a tool for understanding the structure of a network because this is such an important pattern for networks, a macro pattern for networks. It's used in big data studies, and one can find connections and communities that are not necessarily visible in the raw network data. Okay. As Newman says, so an important feature of his approach to community detection is to compare the observed network with some sort of a model. And this is important because whereas much early work in network analysis was concerned about dealing with patterns of ties, Newman's insight was whether that tie is important or not ought to be assessed against a standard. And one of his contributions to the study of community detection is to come up with such a standard. and to look at ties relative to it. So he puts forward a particular measure called modularity, and modularity is high when there are lots of ties within communities relative to what might be expected on the basis of chance. Okay, an important feature of community detection, as I am going to talk about it, is the methods developed are heuristic. Now, many people in computational science would prefer integer programming kinds of solutions or ways of understanding all possible communities that one might detect and comparing a particular finding against the distribution of all possible outcomes. But much of the work in community detection is heuristic. Newman's main contribution has been not actually one, but a family of heuristics for searching for community detection. And a lot of what I'll be talking about stays within the realm of heuristics. So that's a feature of my talk. So here's my agenda. What I aim to do is to separate the idea of community structure from the idea of community detection. So community detection is a powerful way of identifying macro patterning for networks. Community structure is a particular patterning, okay? But there's no necessary reason, this is my assertion, there's no necessary reason that the best macro pattern for a particular network should be one in which there's relatively large concentrations of ties within communities, relatively few between communities, controlling for expected values. And so we can use some of the procedures for detecting community to discover a more broad and in an important sense more interesting range of possible social network patterns. And so the algorithms are really interesting, and they're so interesting that they can be applied to patterns beyond the one that says lots of ties within sets and few ties between sets. Also, community detection, at least as it was originally put forward, was confined to networks of reciprocated ties. So I want to recast this as a problem in directed network ties. This is an area that Newman himself has contributed to, as well as other people, so I'll review some of that. And a directed network, as I think of it, is one example of multiple networks. A directed network means the ties sent are different from the ties received. And so those distinctions need to be made. But in general, we have networks of many different kinds of relations. And so how could we extend community detection to networks of different kinds of patternings, possibly adversarial patternings, as well as the kinds of positive affect or direct connections or functional connections that are always implicitly assumed in a community structure, community detection problem. What if we had networks that were very different from those? And so I want to use, in brief, I want to use community detection as a way to move beyond the idea of community structure defined as more ties within groups and few ties between them. Okay, so if we start getting into Newman's measure, this is a symmetric, I'll deal with his early work. I want to say again, for the record, he's done lots of elaborations that are very powerful and important. In terms of the early work, this is a network of symmetric ties. This is a model for that network. It's the model of statistical independence. Ki is the sum of a row. Kj is the sum of a column. Since the network is symmetric, Ki and Kj are the same. So we look at this matrix B, called the modularity matrix, is the difference between the network ties and what we might expect on the basis of chance. Now, once we start talking about models of chance, there are a number of problematic issues here. Sociologists and other people who have worked with log linear models would think of models that are more sophisticated than the simple gravity independence model. For example, in Newman's formulation, what happens to the diagonal? Typically, self-choices in sociomatrices are zero, coded as zero, but they're not coded as having meaning. But in this measure, he's subtracting zero from an expected value. Perhaps if you're familiar with log linear models, maybe the model of quasi-independence would make sense. We could get expected values for the cells off the diagonal. People who are interested in ergom models, exponential random graph models, which are kind of at the cutting edge of much statistical work with social networks, would recognize this as perhaps not an entirely satisfactory model of expectations for network ties. What if we wanted to control for the number of cycles and so on? Okay, but this is it, and it has a great advantage of being very straightforward. Okay, so this matrix is observed minus expected. Okay, so that's the key insight, and it is an advance because before this, most network analysts didn't take any account of whether the tie you observed was an important tie or not, and this provides a way of thinking about exactly that question. Okay, so in order to find communities, we need some assignment of nodes in the graph into sets or communities. That's given by this vector S. And so, for example, in a two-community model, we'll think about this. So B is this whole matrix of observed minus expected values. Given an assignment of nodes to communities, we can chunk up that matrix and look at sums within submatrices. And so in a two-community example, the measure of modularity is the extent to which there are ties within the sets above and beyond what one would expect on the basis of chance, minus, pardon my typo here, minus the sum of ties off the diagonal with respect to what those would be on the basis of chance. And so this is a measure of the extent to which the community structure macro pattern for a network is realized given a particular partition of the nodes into these two communities. Okay, so as Newman says, to maximize the modularity, we should choose S to be the eigenvector corresponding to the largest eigenvalue of the modularity matrix. Let me stop there and say a couple of things. Some people here aren't comfortable with the idea of an eigenvector, and for you, I would say an eigenvector is a way to represent a full matrix by a single string of numbers, by a vector, in some best way. Just as a mean is a way to represent a string of numbers by a single number in some best way. It also needs to be said that Newman has pioneered, and certainly many other people have joined in creating many different ways to find partitions of all the nodes in a graph into communities. So this leading eigenvector approach that I'll be emphasizing is only one of them. It's one I'll emphasize, although if you like Louvain or other kinds of methods, I think you can translate much of what I'm saying in that more general way. So this is a kind of a spectral decomposition that he uses. And then having computed a string of numbers for this matrix, the matrix being the difference between the observed and the expected network ties, then we can separate on the basis of sign the entries of that eigenvector into two communities. To find a partition of more than two communities, it turns out there's a wide number of ways to conceptualize that and to carry it out. Okay, so let me talk about some issues that have been raised about community structure. So here is a recent article, and the authors note that, in fact, many of the examples that interest us are not just about a single network, but about multiple networks. So how might community structure ideas be extended to modeling networks of different kinds of relations? Okay, and great. This is a general review article in physics on community detection in directed networks, in which there has been a lot of progress made. And the authors point out that in many fields, including many fields represented here, social sciences, biological sciences, computer science, neuroscience, in many actual examples, we're very interested in ties not that are symmetric, but that are directed. Anyone who is a graduate of a secondary school well knows, or is likely to well know, that not all desires for relationship are reciprocated. This is also true of adversarial networks where some people want to do things to other people, not vice versa. So in the world in which we live, there are many aspects of directed ties that we'd like to take account of. And so there's the question of how to modify procedures to get at those. Well, I've stated that as a methodological problem. There's a more important substantive question, which is how we want to think about a world composed of many different kinds of networks that might best be represented by many different kinds of patterning. So thinking about moving from symmetric to directed ties is one entry point into thinking about heterogeneous multiple networks. Okay. There's been a lot of work done recently, Cavella, Mason Porter, and their colleagues that are huge and important efforts to unify the study of multiple networks here under the rubric of multi-layer networks. Sociologists might think about under this rubric things like block models of multiple kinds of relations. They might think about David Krackhart's approach to cognitive social structure, where you have a matrix of who is associated with whom, but you have one such matrix for everyone in the population. Everyone is asked to generate not a row in a sociometric diagram of who their friends are, let's say, but a sense of who you think I's friends are, who you think J's friends are, and you have one of these for every person. So, okay, but these are just two examples from sociology. If we had started including physics and many other fields, there's a vast amount of work, and this team is leading efforts to unify that whole study. And they make a couple of points about community structure in this review of theirs. One is there still a lot about community detection that remains to be discovered. We need to think much more about how to flesh it out and apply it. And then if we want to think in general about structure above the level of nodes, if we want to think about aggregate patterning, we need to think about features of the data besides the idea that the matrix is best characterized by finding clumps that have high propensity to choose within and low propensity to choose between. Okay, so what do I mean by a broader approach to community structure than the pattern that I just emphasized to you? So I'll talk about two examples. One is multiple networks that extend positive ties to also include negative ties. Mark Pachucky and I were having an extremely productive conversation just an hour ago. And it occurred to us that at least in the sociology examples that we're most familiar with, there was often an implicit assumption either that the ties in the network were positive, who likes who, or that the ties were functional, and systems that had necessary connections in order to be glued together to work properly. Once you start bringing in negative affect, things change a lot. This is an example work of Pat Dorian and Andre Mavar on what they called signed social networks. But let me just illustrate the substance here. So if you look at this set and this set, and if we represent positive ties by ones, and if we represent negative ties by minus ones, then this fits the community structure idea for the positive ties. Not everyone in a set is positively tied to everyone else in that set, but all the positive ties are confined within sets. And then some opposite statement is true with respect to these two groups about the negative ties. They are not within sets. There's something about negativity that leads us to expect that they should be from a group to another, from us to outsiders, and reciprocally so. I think I've tried to suggest that here. So if we just look at the red shading in this graph, in this matrix, we see two polarized sets. The hostile ties are between the sets, the positive ties are within. But in this cooked up example by these analysts, they now include something that goes beyond just positivity and negativity. There's this third set of people. They're tied very, very tightly to each other. There are a lot of ones here, but they have in varying degrees some ties to each of the warring factions. This is directed data, but they receive some ties from each of the groups that are themselves opposed, and they send some ties to them. So Dorian and Var say this blue set is a set of people who have the potential of being mediators in this conflict. Not necessarily that they will be, but by virtue of being tied to both members of both sets of a polarized world, there's the potential to link across hostile sets. So my point is, if we think about this simple example from the point of view of community structure is very helpful to us in understanding this and this. It's less helpful, perhaps, in understanding this, and the role of this third set. So why not think about how we can be relevant in that way? Okay. So there's a sense in which negative ties aren't just another example of ties, but they're very distinctively different. So Catherine Giffray studied the art scene in Rarotonga in Polynesia. She was there for well over a year. And to make a long story short, so one of the questions she asked each of the artists doing the network portion of her study was to name the 3 best artists on the island. And many people did that, but many also volunteered the names of the 3 worst artists without even being asked. An important social scientist who theorizes negative ties is Mary Douglas, an anthropologist who basically says that if you want to understand taste, you need to understand what people really dislike. There's a wonderful chapter in her book I wouldn't be caught dead. I wouldn't be caught dead doing such a thing. And that's particularly definitive. So one thing we might say about negative ties is that they're useful in particular for defining boundaries. Okay. So here, in her case, it turns out some of these Rarotonga artists had migrated at an early age to Auckland, New Zealand. Auckland is a major metropolis in the South Pacific. It has the largest Polynesian population in the world. And then some of them returned to Rarotonga. They became known as the Stars in the sense that they received some international acclaim. Then there were the artists who never left, who were native to the island. There was a lot of tension here. Negative ties were concentrated there in such a way as to really define a social boundary in a much more crisp way than positive or neutral ties might be capable of. Okay. There's been a fair bit of work in negative ties in American contexts. Joe LaBianca and Dan Brass look at organizations, managers and organizations in American companies. One domain that makes negativity interesting is in cases where the interactions are in some sense forced or concentrated. Workflow demands hierarchies. And it seemed to Kyle Putz and myself that in some sense that's very much like an island where you can't escape other people. These authors make the point that if you want to understand organizations, how organizations work, it's possible that the negative ties are more important than the positive ones, I think precisely because of the sense in which they define boundaries. Okay. Let me talk about another reason why a broader approach to community structure might be interesting. And this is work in progress of a student of mine, Meltem Odebash, who Sam knows, and myself. We're looking at the data come from Tom Holt. He's a criminologist at Michigan State University. He's an expert in questions like how prices get set in online markets for illegal behavior. So we have access to what is being typed over keyboards in various online forums in which credit card data is requested and sold. And so here's an example of Discourse. This is a subject that came up also as Mark and I were talking earlier today. So we tend to think about networks as having connections that are pretty clear. But if you're a sociologist and you ask people who their friends are, and if you ask me who my friends are, and I say, well, I'm pretty chummy with Barack Obama and the president of my university and so on, I may be telling you something that's very interesting about me, but that's not necessarily an open window into who my ties are. Okay, so discourse, it seems to me, in many aspects of the social world, is not only important to networks, but in many ways it constitutes networks. And so one way to make progress in the future is to put more heavy emphasis on what the language is all about. So here's a conversation in a chat room, and the issue is sometimes what people do in illegal chat rooms, in online forums that have to do with markets for illegal material is issues of trust, as you might guess, are very important. And before buying something, there's the question of how you know that what you buy is going to be any good. And as this writer says, I'm tired of scams. We're looking for credit verification values, the CVV, the number on the back of your credit card. We're looking for large numbers of buying large numbers of credit cards and CVV numbers. They don't always work. Sometimes I pay $10 US for one number, and it's all a scam. Here's my email address. I'll buy it if you give me one to test. And the other person says, don't talk about test free or sample or screenshot with me. If you not trust you can't contact me, then don't not trust you can buy a few little CC to test. In other words, he says, if you want to test some, buy them. I'll sell you a small number, and then you test them, and then you can decide if you want to go through the transaction. What Odebash and I are particularly interested in is how economic theory extends to the kinds of markets that you get online for illegal activity, where problems of trust are important, problems of networks are important. So the reason that this is in this talk is that it's an example of a type of tie that you probably had never thought about with respect to community detection. Okay? What if you were looking for the pattern? What if you were looking for the community structure pattern of lots of ties within, few ties between? How would this fit into that? Here's an example where we code the discourse. So these are various aspects of the users. These are various aspects of the kinds of discourse that they have with each other. They do make positive comments. They do make negative comments. But in particular, they can request a test. And what we think we find is that these ties of requesting a test are particularly likely to come up in these online forums where the requests connect communities that are themselves trusting communities, but they're at the boundary of those communities. So they're in that sense, they're a little more like the way I've described negative ties. They're not within, but between. If you're within a trusted community, you're less likely to request a test that the credit cards you're sold are not a scam, but they connect between established communities. Okay, so this is a second example. So my first example is when you start thinking about negative ties, then the community structure idea needs to be questioned, because it may not be intuitive that negative ties should be within communities. And then my second point is, beyond positive and negative ties, there are all kinds of ties. Requests for tests. Maybe it's positive, maybe it's negative, maybe we don't know, maybe it's both. How can we deal with pattern in a more general way? Okay. In Newman, Newman is truly a giant figure. That's deservedly so. He has thought in his relatively more recent work about issues like how community detection extends to directed networks. He has a solution, which I have to admit works beautifully much of the time, and here it is. It's the same. This is the same formula we had before. This is the observed network. This is the expected. Well, here, in an obvious way, this will be the number of ties sent to a node. This will be the number of ties sent from a node. So if you will, it's a very straightforward generalization of the original idea, where the we can deal with, so this is perhaps asymmetric version of the observed minus the expected, where the expected takes account of the fact that the number of ties sent, number of ties received is very likely different. And so then the measure includes, so now the modularity matrix is directed, but in order to compute a leading eigenvector, we would prefer for some reasons of convenience to work on symmetric data. So we simply add the matrix and its transpose and proceed as above, proceed as before. In this case, we'll compute a leading eigenvector of the matrix plus its transpose and incorporate the asymmetry in that way. It seems very simple. I started out not liking it. I tried it on lots of data. I have to tell you, it works really well. And so that's a very simple extension of a Newman community detection to deal with directed networks. Okay, I'll return to this point. This is, again, recent work where Newman is interested in how different kinds of networks fit together. This is the question I've been talking about throughout the talk, mixture models and how one might do exploratory analysis on mixture models. Now he says something in this particular paper that I found very interesting personally. So Newman writes here that a group is a set of vertices or nodes that have similar patterns of connections to others. And the material in brackets is also in his article. He says the idea is similar in philosophy to the block models proposed by White and others for the analysis of social networks. The citation is Harrison White, Scott Borman, Ronald Breiger, 1976. So he says, well, actually, this new work I'm doing is kind of like shares a philosophy with what these guys were doing a while ago in a different discipline, although the realization and the mathematical techniques used are different. Okay, so this does provide an opening to connect some of the things that Scott Borman and I have long been interested in with Newman's approach to community detection, with an effort to think about broadening the notion of community structure, taking some of the algorithmic ideas but applying them to a more broad view of structuring. Okay, so now let me talk about an example. So I generated some random data. And I wanted to generate some random data that dealt with the situation of negative ties. So in the example I came up with, most of the ties are between communities. So I have 32 vertices. I decided that there are 16 nodes in each group. I decided the expected density internal to each group should be low. The expected density between the groups should be much higher. Threw in a little bit of favoring toward one of the groups. None of these edges are symmetric, they're all directed. And then for aesthetics, so as far as the computer is concerned, is a 1 and a 0. In order to draw these diagrams, I used dotted lines for the ties that were between groups, right? So there's only one network generated. The ties between the groups that I postulated as ground truth, those ties are shown as dotted. The ties within those groups are shown as solid, right? So this is a network. So we're going to take this network on 32 nodes and we're going to put it through the traditional community detection algorithm. And what are we going to find? Okay, well, here's the mean density of the random realization from the ground truth that I just described. And sure enough, there's not so many ties within each of the groups. There's lots of ties between. And what happens when we do standard community detection on that network? So using Newman's approach, we make 15 mismatches. Well, let's see, there's 32 nodes, and so the greatest possible number of mismatches might be 16, and we get 15 mismatched to the groups that I'd assigned them to. So circles, so let's see, in the original, here's the original diagram. So all the nodes in one group are blue circles, all the nodes in the other group are red squares. So here, if we have red circles or if we have blue squares, they didn't match the ground truth. Yes, please.
I'm sorry, am I missing something? I thought that the original Newman approach was intended for communities where you have a lot of connections within, very few across.
Yes, that's right. So I'm applying it to a context in which it wasn't intended to apply.
So in particular, actually here you should be looking at the eigenvector with the smallest eigenvalue, the one that gives you the most opposing Looking at the leading eigenvector is just the wrong.
So that's a very good way of doing a fix, and I want to take your comment and let's include it in the discussion. So you could get a fix here by looking not at the eigenvector associated with the largest eigenvalue, but the one associated with the smallest, because Newman talks about this in some of his early papers, under the topic of bipartite graphs, where by definition the ties are going outside the sets. That's a good fix. There's another good fix that also works here. Instead of doing community detection on the zeros and ones, let's just flip them. Let's make the ones zeros. Let's make the zeros ones.
I think they both have the same solution.
Yeah. Okay. So that's another way of getting to where you started. So there are at least two fixes. And so thank you. It fits in well with the talk for you to make that comment. So I would summarize your comment as saying there's a fix. We can make it work for negative data. Okay? But then what my ultimate comment is going to be, but there are other kinds of data besides positive and negative, and so there could be situations where we're not sure which fix or which set of fixes, which recipe of fixes we would use to fix our particular problem. Suppose the data are asked for a test, or who do you get advice from? Is that positive, negative? I cooperate with colleagues in my department. Is that positive or negative? I think about it. Okay. Okay, so fine. And the fact that we get lots of errors here is a function of the fact that you could say that I'm misapplying the algorithm, exactly as your point suggested, because I'm applying it to data that was constructed with a ground truth that there's more ties between than within. Okay, this is great. Now, oops, that's not good. Oh dear. Oh dear. Okay, let me tell you what this shows. Okay, if I apply, now I did in fact apply Newman's community detection procedure to the data I have as a random realization here, and what happened was it showed that under the partition of nodes that Newman found, there were in fact a lot of ties within groups and few ties between. So as I suggest here, Newman's community detection procedure tends to find community structure even when it's not present in the data ground truth, because that's what it's set up to do. It's a carrot machine. You put something in, you get carrots out. Okay? Now, this is related to what I think is the most important thing I have to say in this talk, which did not occur to me until after a discussion last evening with Professor Borman. So I'm not sure exactly how to attribute this thought. So here it goes. So what we have here is a network that was constructed on the basis of ground truth, where there's lots of ties between groups. We fit an algorithm that intends to find lots of ties within groups, and in this example it succeeds. Okay? So we could say something about which approach is right, which approach is wrong, but let me suggest a different direction. A lot of the game that we play when we do inductive analysis of networks is to find a pattern that's best fitting. But suppose we asked a somewhat different question. Suppose we wanted to find all the patterns that fit at least acceptably well, all the patterns that were good enough. So what does it tell us? That in this particular network, we get a pretty good fit if we try to model the ties between groups, us being strong between groups relative to chance. We get a particular partition of the nodes into sets. If we try to model them into groups that have a lot of ties within groups, we get a different partition, but also a potentially acceptable fit. Okay? So what that says to me is there is a different susceptibility, a word that came up in my discussion with Mark this morning. Structures may have a different susceptibility to reflect either a pattern of positive ties of community structure or its opposite, negative ties. So wouldn't it be great to know the extent to which a particular network had this property of being able to sustain multiple patterns at above an acceptable level of chance? A practical example, suppose we have adversarial groups, okay? Think about violent extremist groups, and the tie might be that they have leadership that had a history of being in the same other group, or they trained in the same camp. So we have ties between these groups. Now the question is, are these alliance ties between the adversarial groups, or are they rivalry ties? Well, suppose you found that an alliance type pattern with ties internal to the groups fit the data, but also acceptably well, a pattern of ties between the groups fit the data. That relates to what I think of as Harrison White's concept of switching. Switching is a property not just of an individual. I can decide to play one role or another role. Switching is applicable in some cases to an entire structure. Is this a structure of cooperation? Is it a structure of rivalry? And perhaps we should be asking a slightly different question when we look at fitting aggregate patterns than we have been. Instead of looking for the single pattern that fits best, what if we got a collection of patterns that fit acceptably well, and that told us something about the degree of flexibility within the structure to be represented in different ways. So a conflict entrepreneur might come along and say, these sets are communities, but I want to turn it into rivalry or something. How susceptible would the structure be to doing that? Nicholas?
So I'm not sure I understood.
Yeah.
I don't know. I don't think I've understood what you've said.
Okay.
But I'd like to take a stab at it. So because there are at least two meanings of it. One meaning has to do with if you vary the type of ties, you get different communities. But I don't think that's what you're saying.
That's right.
I think what you're saying is there might be an intrinsic property of graphs, which we might call groupiness, which is the amenability of the graph to being subdivided into different numbers or types of groups. And in theory, there could be graphs which don't have very much of that. There's just only one way to partition it, and it's just it, like a fully saturated small graph, for example. There's one group no matter what you do. Whereas other graphs might be more groupy. Is that sort of what you're
Yes, it's very much the second. So I've been asked to repeat questions. So do I mean that we can find different patterns for different types of ties, or is there something about the groupiness of a given graph that we're concerned about? It's definitely the latter that I am talking about.
As a property of the graph.
As a property of the graph. Now, I mean, so for example, what many of us are used to doing is we would like to imagine being able to think about all possible partitions. And I'm working with a PhD student in engineering who has some very clever ways to generate all possible block models. That's a separate topic. And so the idea is which aggregate pattern, which macro pattern best fits the data. But I'm suggesting we ask a variant of that question, which is which patterns might acceptably fit the data. Now, one example of groupiness probably has to do with density. If the graph is very sparse with ties, then by definition there must be more ways to partition it into a given structure. One of Harrison White's earliest papers on block models was called Probabilities of Homomorphic Mappings for Multiple Graphs, where he tried to come up with some combinatorics. Given a particular network, what is the chance that each different network pattern fit? Clearly, sparsity of the graph is one dimension, but whatever the dimensions are, it would be nice to take them into account. Please.
I was going to say more than that, it's an issue of statistical significance.
Yes?
So finding a cluster means nothing. You need to say what is the chance you would
Yes.
find an equivalent cluster.
Yes.
So what you've just done in your example is said, the cluster that Newman is producing
Right.
here is not statistically significant.
No, actually it is. I'll talk
Because you
yeah.
gave a random graph.
Yeah,
Okay,
yeah,
if
yeah.
it happened enough times in
Yeah,
a random
yeah.
graph, then you know it is not statistically significant. Because you know it usually appears in a random graph and doesn't relate to the ground truth. I mean, there's a lot of study on that. But if,
Right.
you set up your matrix and make it antagonistic.
Right. Let me go on a little, and then we'll return to this. Okay. So I apologize for the problem with the slides. This is not good. We get a particular modularity value, and what we find is that the numbers in this 2x2 modularity matrix are negative on the diagonal and positive on the off diagonal. No, that's not true. When we apply the Newman procedure, he finds indeed that there are communities. So the numbers on the diagonal are positive, the off diagonals are negative, and so you get a modularity. This may not be all that high. We'll talk about that in just a second. You get a positive number. Okay, so now let me suggest an alternative, and I'm going to go into some significance issues. So the alternative looks a lot like work that we were doing a while ago, but it builds in some ideas from Newman. Let's suppose we have one matrix, call it A. Let's stack A and its transpose. Let's think about columns here. Let's think about the similarity of those columns. One way to measure similarity is the correlation matrix across the directed ties in their transpose. And then let's take a leading eigenvector of the correlation matrix. And I think about the correlation matrix as symmetric in a meta sense, because when Newman thinks about the modularity matrix, he talks about ties within groups versus between groups. But suppose we have a generalized pattern. It may be negative ties, it may be positive ties, it may be ties of requesting a test, it may be ties of advice or who you go to lunch with. We're not quite sure what to do about each of those special cases. There might be a fix for each one, but we don't know what they are. But when we start looking at the similarity across the ties, no matter what pattern they have, similarity in the correlation matrix is consistent with patterning in general. So whatever the patterning is, we're likely to find it. Why look at this measure called correlation, which of course is a very peculiar thing? And my answer to that is given in one of Newman's early papers. So let's think about the covariance. The covariance, if you have, think about the ties sent and received as a binary vector. If you have two of those, you can talk about the proportion of ties in both of those vectors that are 1. You can talk about the proportion of ties in either vector that are 1. And if you look at the probability of being both x and y minus the product of the probability of being either x or either y, that's the covariance. The correlation is a covariance that's normed to vary between 0 and 1. Newman points out the similarity between this idea and his in the modularity matrix. So he says our spectral method for modularity optimization can be regarded as a principal components analysis for networks. And he recognizes the similarity here of the correlation. Now, the specific reason I use it is because I'm interested in symmetry not in the data, but in the pattern, whatever it is, in the data. Okay. So here, using the same example, I'm afraid my slide is going to have the same deficiency. So using this approach, there's one error. Let's see, so the mean density here is consistent with the ground truth. Oh, good. And so the modularity matrix here has negative values for ties within groups, positive values between. It results in a negative value. So since I'm interested in patterning in general, I'm going to choose to think about this in a different way. I'm actually interested not in this sum minus this sum. I'm interested in the sum of absolute values, because in principle, any of these patterns can appear much more or much less than chance, and I want to find out how much structure there is in that sense. So I'm going to propose a variant of this measure, which is the sum of absolute values of these numbers. Indeed, that's what we have here. Now, and I think this relates to significance, let's do 100,000 random permutations on this little example of 32 nodes. So how many of those 100,000 permutations, we'll randomly divide them into two groups. We'll do that 100,000 times. How many of them have a sum of modularity values that are greater than Newman's? Very few. Only 3 out of 1,000. So what the way I'm looking at it, the community structure that's found by applying Newman's approach to this data is statistically significant in the sense that for the sum of absolute values in the modularity matrix, it does better than virtually all random permutations. My approach is pretty good too. And so this is an example of what I'm talking about by, let's think about what the acceptable patternings are that might fit the matrix. So it kind of works. So, and you made the distinction, well, we know there's a ground truth, so we know one is right and one is wrong. But let me question that assumption, because suppose we have something like who gives marbles to someone else. Okay, well, we can construct an artificial example that has a ground truth, but if we're interested in a real network about who shares their marbles with other people, we don't know exactly what kind of relation is generating that. If we find two aggregate patterns that fit, I think it would behoove us to consider that there could be two very different kinds of structures involved. And then again, from a Harrison-White perspective, this might help us to understand how some structures can flip into their opposites, for example. please.
I was going to say, there's one issue with using these sorts of p-values,
Yep.
which is you have to compare against the number of hypotheses you've tested. And when you're using an algorithm,
Yep.
that has actually ruled out an exponential number of hypotheses in your graph.
Right.
So unless you're being really, really careful, you got to multiply this by 2 to the number of vertices in your graph, and your p-values usually become more than 1, unless you're really careful.
Okay.
So,
Okay. So that's a serious comment. So I would like to talk to you more about
sure,
improving
yeah. So
my
you-
thinking about
one has
that.
to be very careful with p-values for
Okay.
modularity.
Okay.
Or anything where you have an algorithm.
So, okay, so thank you, and I want to learn from you about how to do that better, but I want to go back to your main point. How do you feel in general about the idea that there could be different macro patterns for the same data set, and that the analyst could find that to be really useful information?
I'm a big fan of that idea.
Great, thank you. Nicholas?
Yes.
So, related but a little distinct from that,
Yeah.
I mean, another way to sort of conceptualize or frame what you're saying is an old argument about social structure, which is, you could map the social networks in this country 300 years ago, and 200 years ago, and 100 years ago, and today.
Yep.
So all the incumbents in the role are all gone, but the structure is the same.
Yes.
Which is a claim, of course, we've been making in other work of ours about
That's
the
very
importance.
cool.
So the idea would then be, if I've understood the intellectual part of what you're saying, is that, even in the picture you drew, by the way, if you didn't put the circles and the squares,
Yeah.
I could look at those two graphs and say, oh, Newman discovered the structure that was there. The
Mhm.
algorithm worked.
Right.
It just missorted the nodes, but who cares?
Right.
Actually partitions it into two, groups
Yep.
with
Yep.
these
Yep.
properties.
Yep.
And so in a deep sense, what you could say is that actually there is some intrinsic structure regardless of who occupies the slots. Is that what you're saying?
I'm not sure, at the end, I wasn't sure what you meant by some intrinsic structure. It seems to me there's multiple intrinsic structure.
What I meant is that let's see how to put this. That I'm asking, are you arguing that there are multiple ways of discerning structure in a social system, all of which are compatible, even if the individuals within them are sorted to the wrong groups?
Thank you for that question. So the question is, are there multiple ways of discerning social structure if the individuals are sorted into different sets of groups? Okay, so let me focus our attention on this idea of discerning structure. Okay, so who discerns structure? One possibility is that it's the analyst who discerns structure. And often when we talk about that, we want to find something that fits best against some significance test. But another way of discerning structure could be that the actors in actual social networks might contend over the patterning of that structure. So they might say, the sociologists and the political scientists should unite against the chemists and the physicists because they have more in common or something, right? Or some other person might say it should be the older disciplines versus the younger disciplines. So I'm interested in particular in that second sense of discernment where the discerning is being done by actors, some of whom might be entrepreneurs about what the structure should look like. Who should our enemies be? And so on. And so I guess the question I'm asking is how much leeway is there in a structure to allow actors to redefine that structure to be the opposite of what it appears to be. So one day everything is very cozy and we have these communities and they coexist, and the next day they're subdivided in a very different way. Perhaps there was a violent event between yesterday and today and people have reorganized. How much does the structure facilitate the possibility of that kind of reorganization? And I think, so one way of proceeding on that question could be to have a catalog of possible macro-ideal type structures to find some way of testing all of them. Now, of course, you could brute force it and look at all possible partitions, but another way to go might be to have a heuristic for each one. So Newman has a brilliant heuristic for community detection, doing it on the inverse of the data, the complement of the data might be a way of getting at negative ties. If we had a series of heuristics, we might test each of them against a given data set and come up with something about the degree of variability in the structure. Does that make some sense? We'll go back to it. Okay. Okay, so this is matches to ground truth, and obviously this comes out the way it does. I'm not going to proceed that. I have a second example, which I'm going to skip. In this example, we have a core periphery structure. The same qualitative findings are found so in a core periphery structure, there's, I'm glad I'm going to skip this, there are ties within one group and ties in both directions from that group to a second, but the second group has very few ties among itself. Applying Newman's approach, we find a pretty good community structure representation. Using my approach, we find the core periphery structure that I intended to build in here. Let me go entirely through that. Okay. It seems to me there's a way to extend it to multiple networks in this way. Here's the example from Dorian and Mavar that had the two polarized groups here, the red and the blue, and these people who could be mediators in between. The first, the leading eigenvector splits them here, but then a subsequent split suggests that these people, while they have a lot of ties to the red group, also have ties to the other and so on for the blue. One way of seeing that is to look at correlations on the correlation matrix and so on. There's a wonderful reference here of a statistician who has done that. So if you look at the correlations of the correlations of the correlations, you start seeing a pattern that's veering toward a split into two groups, but it hasn't quite gotten there yet, and these people capable of mediating are in between. Okay. Let's see, it's just about an hour. Let me tell you what I had intended to do. How about 5 minutes? Okay, so this is some work that I've been very much involved in for the past few years. One person who's joined me on this is Lauren Pinson, who, are you here? Is a PhD student at Yale in political science, was a project manager on a data set. So let me just say what this is about. I claim that these ideas about community structure are very relevant to the workhorse of the social sciences, regression analysis and its generalizations. Let me just give you an example. The outcome variable here, well, the units of analysis are 108 violent extremist groups. The dependent variable is whether they were coded as having used or pursued chemical, biological, radiological, nuclear weapons during this time period. Because the dependent variable is 0, 1, we do a logistic regression equation, and that's kind of standard. 11 predictors, for example, what's the age of the group, how many attacks, are they state-sponsored? The dependent variable is, did they pursue unconventional weapons? We do a conventional analysis. Now, it turns out that inside regression analysis is a network. It's a network among the cases. So we usually define regression as the study of the network among the variables, but regression analysis has a dual. There is a network among the cases. Now this is actually widely known, although not very widely appreciated. So if I call this matrix the hat matrix, raise your hand in network diagnostics, the hat matrix is very important. The main diagonal of the hat matrix gives you measures of the extent to which a particular point may be an outlier. We're very interested in the off-diagonal entries as well. And again, this is a known result, but let me just tell you about it. Y hat here is the predicted value of the log odds of pursuing unconventional weapons, log of p hat over 1 minus p hat. These are exactly, to any number of decimal places, the y hats that would be produced by the standard model when you push the compute logistic regression button. These are the pseudo values, so I'm going to just say that they're very much like the observed values on y, and this is this matrix. And so here's a way of restating the regression model. The predicted value for this first group on y is equal to the observed y value for every group times each group's similarity to the first one. Okay, that's not the way we were taught regression modeling, but it's true, and it's a way to represent regression. Many of its generalizations here are logistic. Okay, so it would be nice to do some sort of community detection on this matrix, which is generating the results of standard regression modeling. And so it turns out that matrix itself can be decomposed into distances from the origin. Think about this as in a geometric sense. There's the extent to which each group is distinctive, has a distinctive profile across the 11 variables in this regression model, and then also cosines. So any particular number in the previous matrix is just the product of the two distances times the cosine. Cosine is a similarity measure. I won't go into it, but these two groups indeed are similar. These two are similar. They tend not to be similar between. So doing community detection on this matrix has a lot to do with what we find, what we learn when we run a regression model. And it would be fun to understand communities among the cases as producing regression outcomes, which again is very important, although I don't think any of us were taught regression modeling in just this way. This is a graph of the cosines that are large. The organizations that tended to pursue unconventional weapons tend to stand out in a conventional spring in better representation of the cosine matrix binarized in this way. Here we don't binarize, we look at the first two eigenvectors. And here, suppose we wanted to find some sort of a basis space for the space of these violent groups. We might choose ones that are in the kind of opposite sides of this diagram. So I picked these two. This is Lashkar-e-Taiba, a Pakistani group that was involved in the Mumbai attacks, Hamas, Jemaah Islamiyah in Indonesia. So what we can do for each of these groups, we can say, well, what are the 8 groups that are most similar to them in these 3 groups? And what we find in this example is, of course, there are 24 groups here. There's 8 most similar groups to each of these 3, so that's 24. But of those 24, 20 are unique groups. So that's to say that picking these groups kind of spans the space of profile similarity in a way that's pretty complete. And then also it tends to include on the outcome most of the groups that we're interested in finding. And so what I'm trying to suggest is that there is a dual to regression modeling. And fundamental to that dual is a matrix among, or network among the cases, and finding communities of cases in that matrix that yields the expected values on Y, gives us insights into how the regression analysis is produced that aren't available in conventional interpretations of the exact same regression equation. So I guess this is one way of getting into adversarial modeling using community detection, but at a kind of a meta level. I think that's where I wanted to end up. So I think my main points were community structure is a particular pattern for a social network. It can and we ought to untangle it for algorithms used to find community detection. So in fact, using community detection algorithms, there's a very broad, rich, important, interesting, diverse range of possible social network patterns, and it would be nice if we could find them. So community patterning of a directed network, this is a subpoint. If we have a directed network, it's actually thought of as part of the analysis of multiple networks. So in that sense, we can use community detection to move beyond community structure. Thank you, and more discussion. Okay.